Hello, I'm Omnik. I will be solving together beginner contest and I will try to explain what I'm doing. As always, I expect first 2-3 problems to be not problems. Given a string, print the position of the only uppercase letter in that string. Yeah, I think I can do that. Problem B. We have 5 n judges. We should ignore n highest grades and lowest grades and calculate the average of the remaining 3n grades. Sure. Yeah, beginner contests are too beginner for my taste. But hopefully next problems are not that easy. Problem C. He made m moves, but the n moves are represented. Okay. Okay, so we are given moves right, left, up, down. Determine if Takashi visited the same coordinates multiple times, including start and end points. Just yes or no? Okay, so just like implement exactly what's written and put all the coordinates, all the points we visited in a set. Okay, so problem C is also not interesting. So if we never visited the same coordinate twice, the size of the set should be n+1. So we print no, I think. Otherwise, yes. Or maybe it's the opposite. or problem D. And cards line in a row. Each card has one number on the front and one number on the back. Those numbers are given. We can flip some cards. There are 2 to the power of n ways to do that. And we need to calculate number of ways that when the cards are flipped, for every pair of adjacent cards, the integers written on their face-up sides are different. Well, that's an obvious dynamic programming. So we arrive at some point, we have either flipped that card or not. So that's our state, and we want all the previous cards to satisfy this property, so that no two adjacent numbers are equal, and we calculate everything. Well, that's at least like a problem. First three were not problems like in any in any sense. So we're iterating our cards, looking whether we flipped, like what side we have chosen for the previous card, for this card, and if they are different, we can actually make this transition, and we should say that dpiy should be increased by dpi minus 1x. Because, well, every way from that position can be continued using the side y. Problem E. So there is a permutation, but I guess it is not given because we should find it. You don't know A, but you know some comparisons. Can A be uniquely determined? If it is possible, find A, and it's guaranteed that there is an A consistent with the input. Well, that sounds like find topological ordering, right? We are given directed graph. For every such pair, we say that, okay, there is an edge from position xi to position yi. That means that in that position, in position yi, the number is bigger than in position xi. That's such permutation is literally the topological ordering, and we should check if there is only one topological ordering. That is done by finding the topological ordering and checking that for every consecutive vertices there is an edge from the left one to the right one, because otherwise we can swap them, and that will be also a valid topological ordering. So we will find topological ordering with DFSs. I don't know the name of the algorithm, but like finding topological ordering. Now we are checking all pairs of consecutive vertices in the topological ordering. And among the neighbors of V, there should be X. If not find, that means that we can swap them and we should print like no or something. Otherwise we print yes, and we should print the topological ordering, but like we need to print the permutation A, which means that we should like take the inverse permutation of the ordering we have found. Like I have found the order in which vertices should go, but I need to find which numbers are written in the vertices. So problem F. Looks like another graph problem. Have n vertices, one-way teleporters, so like directed graph. Whether a teleporter can send you from city I to another is represented by a length m string Si consisting of zeros and ones. So we can only move forward, and we are given which forward edges exist, and we can only move on at most 10. So at most m, and m is at most 10. Solve the following problem for each k. Can you travel from city 1 to city n without using city k by repeatedly using a teleporter? If you can't print the minimum number of times, you need to use a teleporter, otherwise print 1. So for every intermediate vertex, we should solve shortest path from 1 to n if it is not allowed to use this vertex. Well, we can only move to the right, and all of our jumps are of length at most 10. So we can find, we can run BFS from vertex 1 forward, from vertex n backwards, like using reversed edges. And now when we want to solve for some vertex, we need to, like, there will be an edge that jumps over this vertex. It will be unique, and there should exist such an edge. We can just iterate over all of them. All of them should start before this vertex and end after, but that means that they're only like m squared candidates, right? Like the length is at most m, so m squared over 2 actually. And if we use this edge, the shortest path using this edge will be like arrive from 1 to the start of this edge, and then from the end to n. But that means like that's the same as from n to the end of the edge using reversed edges, and we cannot like accidentally visit the blocked vertex on those like first and last half. because we can only move from left to right, so like both start and finish are on the same side of the block vertex, so we cannot visit it even if we wanted. Yeah, that would work in n times m squared. We run BFS in n times m because that's the number of edges. That's actually like we can do it not with BFS but with dp, because again we move only in one direction. Yeah, and then just for each vertex calculate the answer in m squared time. All our distances are well, at most n, so big N can be infinity. So A will be the distance from the start to every vertex, and B is the distance from the end to every vertex using the reversed edges. So yeah, here we should be accurate. We should use inverse edges, but they're not stored for this vertex. They're stored like there, but we still can iterate over the length of the edge. It will be at most m, and thus if this edge exists, it goes from v minus I on length I, and I should add this check because yeah, I don't want to look at the vertices that do not exist. Or I could like write dp backwards, then it will be easier, I guess. So we initialize answer with infinity, and now just try all the ways to choose an edge that jumps over vertex v. That's how much I will go left and how much I will go right. If this edge exists, which is an edge from v minus I on distance I plus j. So I should reach the starting vertex from the start, plus traverse this edge, plus from the end of the vertex reach finish. That's written here. Here I should print something like -1. Yeah. Alright, and problems G and H are usually not that easy. Problem H is usually about some standard technique which is not easy at all. But first let's look at problem G. 8-second time limit. So we have two arrays. Well, elements are like of length 5-bit, I guess. Perform the following operation on A any number of times, possibly 0. Apply a left cyclic shift by 1. Okay, so that just means that we choose a shift. Objective is to maximize the sum of like coordinate wise or. Okay, so we shift A, choose some to click shift, want to maximize sum of or. Can't we just calculate it for all shifts? Like, all bits are independent. So 5 times I want to calculate the thing for arrays of zeros and ones, right, for each bit, for each cyclic shift. But that just means like for each cyclic shift it's just not total number of ones minus the number of ones that will be in the same position, and that sounds like FFT, right? We want to calculate convolution. That just works, right? And it looks like it's intended. 8 seconds, 5. that just looks what they want. Okay, this is a bit weird. I would expect like this problem to be problem H. It's an educational problem about like FFT can be used to calculate something for all cyclic shifts. But it's not an interesting problem. Okay, so my library says that I should check log. Let's do that. So log is a constant that will say like up to which length we can calculate F15, so like the product of two polynomials. So 2 to the power of log should be greater than maximum degree the resulting polynomial can have. So I will reverse A and then just multiply those two. Looks okay to me. So like the degree will be up to 1,000,000, which is smaller than 2 to the power of 20. So I said that or sum of ors will be just number of ones, which is calculated as sum, minus sum of ends, which will be calculated using FT, because like end is the same as just taking product. So we want sum of products with shifts, but after reversal, that's just convolution. Like usually you need to be careful about like after reversals and shifts and stuff, like what is exactly written in position I, but here like any shift is okay, like as long as I'm consistent between different values of k, like each I will correspond to some answer and I just need maximum of them, so it doesn't matter in each in which like order I calculate. The leap is big. Okay, and the last problem, we have a tree. To construct a rooted tree R, satisfies the following conditions. If the lowest common ancestor in R is Z, then vertex Z is on a simple path between X and Y. In R, for all vertices V except for the root, the number of vertices of the subtree rooted at V multiplied by 2 does not exceed the number of vertices of the subtree rooted at the parent of V. Did it like swap the order of G and H? Because well, G is educational problem, and this looks like a just a problem, and I would be surprised if there is like some known way to do that. Well, maybe. Okay, so we are given a tree and we are asked to construct a similar rooted tree, but it should be balanced. Similar in the sense that like for two vertices, their LCA and in the tree we have to construct also was on the simple path between X and Y. Isn't that like construct centroid decomposition? I can choose centroid in the initial tree, make it root, then recursively construct the tree in each component and connect the roots to the centroid. Then for any two vertices, their LCA is like the lowest common centroid, and centroid lies in the path between them. In this case, and this property exactly means that it's a centroid. Okay, so it's kind of an educational problem, but I still think that this is an actual problem, and G is an educational problem. But yeah, this problem asks to construct centroid decomposition of the tree. What should I print? Parent for each vertex and -1 for root. Okay, can do that. So I will do it in the following way. I will fill the answer with -1s in the beginning. And then when I find the centroid, I will set the answer to all the vertices in like the current tree except for the centroid to be the centroid, and then do recursive calls in all other components. Then like I don't change the answer only for the next centroid, so its parent will be the previous centroid, and everything else is correct recursively. Function solve takes some vertex of the current tree for which I should solve. It will first find centroid for the component, and then it should like set the centroid to be v, like set the answer to v for every other vertex. So I'm iterating over the neighbors of v if they're not bad, which means that like I will mark as bad vertices that were deleted, like previous centroids. So if it's not bad, then it exists, and I should like dfs ans uv v. So for this vertex with this parent, set answer to like everything you can reach to this. And then just call solve from, since that's it. And in all DFSs that I will have, like I'm traversing the edge if it, like this vertex is not bad, and I'm not going back to where I came from, the parent. So in find centroid, I should calculate sizes. And then go to the largest sum if its size at least s over 2. So if in which cases this vertex is bad. Well, if it is bad, it means that it doesn't exist, or it is my parent, but that means that its size is strictly greater than my size. That's when it's bad. It's good. If it is big enough, I should go there. interesting. Not bad of you. That sounds right. Okay, so easier than usual, I think. Beginner contest. Yeah, I can't say that any problem was that interesting. But yeah, the last three are kind of education. So in F, like this cool idea that if you block something and like you have linear order, then there should be a unique place when you jump over the blocked thing, and you can just try all the possibilities. Like, I think this problem would be easily solvable like without this limitation for any duck. Like if we know that edges are directed from left to right, we can do exactly the same. The only thing that is not that easy is okay, for a vertex we should iterate over all the edges that like jump over it and take minimum of values corresponding to those edges. Basically, like for each edge we calculate the minimum path that going through that edge, and that we can do for any duck always. And now we need to take minimum of them, but there can be a lot of them. So it's like of nm in the worst case. But we can like inverse the order of operation kind of and say that okay, let's initialize answer with infinity for all the vertices, and then for an edge we should say okay, for all the vertices that we have jumped over, we should update the answer with the shortest path, length of the shortest path that pass through this edge, and that's like minimum on segment, mean equal on segment. That can be done with with segment 3 for sure, but I think you don't even need it, because you only need to like set mean m times and then find the final state of the array. You don't need to be able to calculate the values at some point, so you need to like apply all updates and then read all the values. So that can be done without segment tree with the same complexity, either with like scanline with set, kind of like remember that you need to like apply mean on the segment, and you say okay, in the left border I will remember that like until I say so, the answer should be at most this value, and then in the right border you will remove this, and so after that you will do scanline with set. When you like encounter start of a new segment, the set will basically contain all the values for edges that go over this vertex, and so you take minimum of them when you traverse the vertex, and when you arrive at the beginning of a segment, like you add new value to the set, just insert it, and in the end you can remove that value from the set. So that's like n plus m times log. Or there is a very nice idea, like you can do like sparse table but in reverse. So like what's the idea of sparse table? You have these levels with like they correspond to segments of lengths that are powers of 2. And there is like a segment for every starting point with the given length, right? And suppose you want to like do many mean on segment and then collect the results. So what do we usually do with sparse table? If we have a query, like we find the largest power of 2 that fits inside this query, cover it with like 2 segments of length of this power of 2, and well, instead of doing like mean equal some value on this red segment, we can do mean equal like on the 2 segments of length of power of 2. That will have the same effect, right? We changed the values in the same positions and we changed all of them. So like for each query you just need to change 2 positions to like, remember that in those 2 segments like you should do mean equal. So after you do all the segments you can like push those updates down. So when you have like this segment of length power of 2, you can split it into 2 segments of smaller power of 2 and like push the value from this segment to this segments. And so you start from the highest level, and for all the segments of length power of 2 you split this update into 2 and update like 2 smaller segments. Go through all the levels from highest to lowest, and in the end in each position you will have like the minimum value that you want. So that works in like if q is the number of updates and n is the length of array. So each query is constant time plus n log n, because you have log layers, and on each layer from each of the n, at most n segments, you do constant number of operations like pushes down. But it requires n log n memory, which is like the only bad thing I can say about this thing. So yeah, that's like this sparse table like solution. Then there was scanline with set, but because like you do operations with set, that's q plus n log log q actually, but doesn't matter probably. Time, but linear memory. Set. And as always you can overkill with segment 3. That's I guess n plus log n time and n memory. segment tree. But yeah, no. Well, segment tree is not hard per se, but it usually requires writing some code. Even if you have like pre-written segment tree, you still need to like adjust the like, types and operations you have, while those things are very easy to write, and especially like this one is like basically the same 10 lines you write when you write sparse table. I like this solution very much. The only bad thing is that it requires unlock in memory. Alright. So that's problem F. Problem G was about the fact that cyclic shifts equals 50. Kind of. So like when you match with, want to calculate something for all cyclic shifts, it means that like for a fixed cyclic shift it means like we should match like this, but if you reverse one of the arrays it will be like matching like this. So with fixed sum, like one coordinate increases and the other decreases, and that is like exactly convolution. So you just write the 50 and it works. And problem H was about like just understand that what's written here is the definition of centroid decomposition, and then construct it. Yep. I guess that's it. Thanks for watching. Goodbye.